Hi there, and welcome to Laser Classrooms, Bringing STEM to Light. This is Module 5, and it's presentation number 1. And here we're going to take a look a little bit deeper into reflection. We've been looking at reflection, and we know that the reason that we can see things is because the light that comes from the sources around us, the sun, the light bulbs around us, it interacts with the materials around us, and it's either absorbed, transmitted, or it might be reflected. And what we see around us, for the most part, is light that's reflected off of objects and into our eyes. And here we're going to go a little bit deeper into a specific rule that reflection follows in all cases. And we're also going to take a look at the question, why do some surfaces create a reflection like a reflection that we think of when we hear the word reflection, right? I mean, most of you probably didn't think light is reflecting all around us all the time very much before we went through it. You thought of a mirror, right? And a mirror reflects in a very different way than the objects around us. Otherwise, we'd walk around and see our reflection in everything that we encounter. And we don't do that. And why would that be? Well, first let's take a look at the rule that reflection follows. It follows a really specific rule. It's very simple. When light hits a surface, it comes in at what's known as the incident ray, and it hits the surface of the object, and then it bounces. It bounces away from that object. That's reflection. And it just so happens that it follows the rule of reflection, which says that the angle of incidence equals the angle of reflection. And all that means is that relative to the normal, which is that red line right there in the center, relative to the normal, which is perpendicular to the surface that the angle of incidence, or excuse me, the incident ray hits, the angle of incidence equals the angle of reflection. So it's going to come in at one angle, it's going to go out at another angle, and those two angles are going to equal each other. And there is a great way for you to use the equipment, either the light blocks in your kit or the flashlights that you've set up with a ray of light and a mirror. You can do a little demonstration / activity to help students uncover the law of reflection. And we'll take a look at that now.
So now we're going to look at reflection. It turns out that light reflects off of a surface in a very specific way, and this activity is designed to help your students uncover the law of reflection. So let's take a look at that. For the reflection lesson, we're going to use one light box with the line cap on. I'm going to use the red one. And we're going to use a mirror and your mirror clip. And then we're also going to use a protractor. The first thing you want to do is position your protractor. We're going to have our protractor facing a specific way. We're going to have the 90-degree mark going across like this, and we're going to have that 0 and 180-degree mark pointing directly towards us, and that's going to be the center right there. And then you're going to set up your mirror with your mirror clip. And if you squeeze the edges of your mirror clip, it will open and you can insert your mirror. You're going to position it like this so that it stands flat on your protractor. And we're going to place the mirror right along that 90 degrees, so it's 90 degrees on either side, and 0 degrees is right in the middle. And we're going to divide that mirror so that the center point is right at the 0. And the first thing you're going to do is turn on your light blocks and just get an intuitive sense for what's going on. So we can point that ray directly at the middle, and we can see right away that there are now two rays. The first one leaves the light blocks and strikes the mirror. That is called the incident ray. And then immediately when it strikes the mirror, it reflects back out, and that is called the reflected ray. And if you move your incident ray, like change the angle at which you shine in your incident ray from either side actually, you notice that that reflected ray moves at the same time. And we're using a protractor here, so we're going to actually measure some angles, and we're going to find out exactly what the relationship is between this incident ray and this reflected ray. Because once we do that, we will have figured out what the law of reflection is. And the first thing you need to know is that this line right here, it's kind of an imaginary line that runs along, in this case, along the 0 degree mark, perpendicular right from the center of the mirror towards you. We're going to call that the normal line. And you're going to measure the angle between normal and the incident ray, and that's going to be called your incident angle. We're also going to look at another angle, the angle between normal and the reflected ray, and that's going to be your reflected angle. And there's a relationship between the incident angle and the reflected angle that is very consistent in the way that all light always reflects all the time. So we're going to take some measurements and see what that relationship is. So we're going to start by placing the light blocks so that it shines right along that 30 degree mark, directly to the center of the mirror. And it does diverge just a little bit here. So it's a little bit wider when it leaves. Remember how light spreads as it travels? We're experiencing that here. We're going to do our best to get it lined up. I'm going to see that it comes in along the 30 degree mark, which means the distance between normal and the incident ray, that is an angle of 30 degrees. And as it exits the mirror, it also passes directly through the 30 degree mark. So the angle between, or the reflected angle, the angle between the normal and the reflected ray, is also 30 degrees. Let's see what happens when we change it to 60. So we have the incident ray coming in at 60 degrees, which makes our incident angle 60 degrees. And then we have the reflected ray leaving also at 60 degrees, which makes our reflected angle also 60 degrees. And that is the law of reflection. So the law of reflection says the incident angle is equal to the reflected angle, and that's always true. That's how light reflects.
So that is the law of reflection. The angle of incidence equals the angle of reflection. So how can we use our understanding of that to understand why we see a mirror image in the lake, but we don't see a mirror image in the field in front of the mountain on the right? Well, it has to do with the way light bounces off of particular surfaces. So the lake is a very, very smooth surface. At least it is on this day, right? It looks like there's no wind, and we have got just a beautifully smooth surface. And what that does is it causes, right down to the molecular level, all of the surfaces off of which light could possibly bounce to be at the same angle, right? So it's very, very flat. There's no roughness to it whatsoever, or very, very little. Now, if you imagined a boat going by, or perhaps a storm coming along, you would not see that same image there. You would have a rough surface, and that would cause light to bounce in all different kinds of directions. And that is known as diffuse reflection. So that's what's happening with this picture here, right? So in the previous picture, light was bouncing from the sun onto the mountain and into our eyes, but it was also bouncing from the sun onto the mountain and down onto the surface of the water. Well, the same thing is happening here. Light from the sun is bouncing off that mountain down onto that field, but guess what? We don't see a reflection of that because the light is scattered in so many different directions. On top of that, the material that this light is bouncing off of is also absorbing a whole bunch of the light that's bouncing off that mountain and a whole bunch of the sunlight, which is why we got color, right? Because of the light that's absorbed. We're only getting the frequencies that aren't absorbed. But the main reason we don't see a mirrored reflection in everything around us, even though all we're seeing is reflected light, is because all the surfaces, except for a very few, are actually quite bumpy or rough, and that's what gives us the appearance of texture And that's what causes that light to not actually create a reflection of our face. And, you know, we're talking down to the molecular level. So even what seems like a very flat piece of paper, if you were to look at it under a microscope, you would see that it's composed of lots and lots of little tiny fibers. And those fibers are at all different kinds of angles. So if you were to bounce the light off of something as rough as a piece of paper, you would get a smooth appearance, but it still wouldn't be smooth enough to reflect your image back to you. There's a great analogy of this with dropping simulated photons. We'll use ball bearings as photons, and we'll take a look at what happens when those ball bearings hit a very, very smooth surface versus what happens when they hit a very rough surface. What do you think is going to happen? Let's take a look.
When we drop ball bearings on a smooth surface, like this piece of tile, they bounce straight back up at the same angle that they hit the tile. And when we drop them on the underside of a tile, the rough side, they scatter.
So that concludes this presentation on reflection. The next video that there is to watch is a really great modeling activity for modeling reflection, and it involves using very familiar objects and seeing how reflection works. So take a look at that next, and I will talk to you in the next presentation.